The Earth is warming faster than ever in human history. Ecosystems are shifting and wildlife is forced to adapt, migrate, or else risk extinction. To protect species, ecosystems and us, we need to know how life handles rapid climate change shifts. Luckily, Earth has seen rapid climate change before and left behind some detailed records. One of the best examples comes from ice cores in Greenland and sediment in the northern Arctic Ocean. These records tell us about Dansgaard-Oescher events, or DO events, when parts of the planet warmed drastically in just decades. They started suddenly. Within 10 to 20 years, Greenland's temperature rose by 8 to 16 degrees Celsius during the last ice age. Imagine today's global climate crisis, just 10 times faster, but on a smaller scale. It is still unknown what caused these sudden rapid warmings. There are 3 theories, but the leading theory is abrupt changes to the Atlantic meridional overturning circulation, or better known as AMOC. This is a system of ocean currents that moves warm, salty water north and returns cold, dense water south. The Atlantic stream of the AMOC differs during the years. Temperature, ice and density of the seawater influences the AMOC. Right now, warm water flows north. There it cools down and sinks to the bottom. This happens because cold water has a higher density than warm water. Because the cold water sinks to the bottom, it flows back to the south and warms up again. This way the cycle starts over again. What happened in Greenland during the DO event was different. There was an ice age which caused a lot of formation of land ice and little meltwater. Because of this, the water did not cool down and the Atlantic flow stopped. It started again when the water became salty enough that it started to sink again, which created a water flow and the AMOC started again. The new flow brought even warmer water with it, which made Greenland rapidly warmer. The AMOC causes rapid warming after a cooling period. This rapid warming causes DO events. This on and off pattern repeated over 20 times in the last ice age. And it wasn't just Greenland. We see signs in ocean sediments, ice rafted debris, and plankton fossils all across the North Atlantic and Arctic Sea. Right now, this oceanic flow is slowing down, and melting ice is a major reason. The vast Greenland ice sheet is pouring a lot of ice into the ocean each year on average, and it's accelerating as the planet warms. This influx of cold, fresh water into the sea can destabilize the AMOC's flow over time. Because of this destabilization, many European regions will cool down. DO events give us a rare window into how species in Greenland responded to the changed ecosystem due to rapid warming. After each DO event, ecosystems didn't just change, they flipped completely. This has an effect on species across all trophic levels. Species better adapted to warmer climates became the new dominating species. Forests surged northward into previously frozen terrain. Large mammals suffered large population losses and loss of genetic diversity, while smaller, fast-reproducing mammals often proved resilient, sometimes even increasing in levels of biological diversity from genes to organisms and ecosystem genetic diversity. Not every ecosystem could keep functioning through this chaos. Some lost their fundamental functions. These ancient climate flip switches offer us a preview of what might happen as humans accelerate warming today. Analyzing DO events can help us understand how certain species will react to rapid climate change. So, what can these ancient climate shifts teach us about our warming world today? While DO events were regional rather than global, they reveal that nature has a remarkable but limited resilience to rapid climate change. The evidence is clear. Life can adapt over time to a changing climate, even to dramatic shifts. That's our sliver of hope. The challenge? We've added obstacles previous species never had to face. Cities cutting migration routes, farms replacing forests, and roads blocking wildlife corridors. But by studying which ancient species survived these climate sprints, we can gain more knowledge about their ability to adapt and give biodiversity its fighting chance.